maxima, minima. Now, maxima, minima is the last application topic for your notes. Okay, so this will be the last part of topic 3. After which, then the next few lessons we will start to clear the AFL as well as the practice set. Okay, okay, so shut up. Okay, so from here, differentiation techniques, higher order derivatives, increasing and decreasing function. These were the things that we went through the last time around. If you remember the last lesson, what did we do is we went through the nature of stationary point, how it can be a maximum, minimum, or as well as a Hall fraction. We went through the fact that we can use the first or second derivative test. First derivative test, we draw a 3x4 table. The second derivative test, we basically differentiate. If the second derivative is negative, that gives us a maximum. If it is positive, it gives us a minimum. If it goes to 0, then it is inconclusive. You know, some people may find that, hey, second derivative, sometimes don't work there. Then what I still use? Might as well I always use first derivative. That's up to you. So those who do H1 math, some of them they don't do A math O level. They actually don't learn second derivative. They use first derivative all the way. Right? So why do we still learn second derivative? Simply because sometimes if your functions are easy to differentiate a second time, then I just use second derivative. Easier, but it's faster than drawing a 3x4 table. Okay, no? Sometimes if there's a shortcut home, you will want to take the shortcut. But sometimes it's risky. You might be a robber. Right? So a long cut of course is safe. Okay. So we are going to we have learned quite a few application topics like higher order derivatives, increasing decreasing function, stationary point. And now we are looking at the real one, which is maxima minima. Okay, maxima minima for this topic as well, you will need to know. You need to know the formulas for surface area, volume, cones, spheres, all those stuff. Okay, can which is under your JH1 topic. Yeah. So derivatives and stationary values are useful in everyday situation. Examples of fields that require such process include aerospace engineering, civil engineering, and hacking design problems. University, they actually study something called optimization problem. Yeah, it's optimization problem. Optimization problem basically is that you're finding the highest. For example, during my uni days, we actually go and study, but in uni is different. So like I went to the McDonald's restaurant. So like for example, profit and the number of tables, number of two-seater versus number of four-seater, there are a few variables. Okay, we actually have two variables and we find the maximum point. Right, there's a sweet spot of number of two-seater and four-seater that can give you the maximum point. Yeah. So differentiation actually, of course in real life in college we use computers to do the optimization, but in day-to-day there are actually things that we use. For example, they can use this to calculate another thing is calculate, for example, the number of seaters in the airliner. For example, if you give you a Singapore Airlines, right? How many business class seats should I have? Which number will give you the maximum profit? How many economy seats should I have? Which number will give you the maximum profit? So all these are actually under differentiation. Okay? So if you learn higher mathematics this time or you have seniors who learn mathematics, whether you do engineering, computing, even life sciences, you are going to do stats, you are going to do differentiation. Yeah, okay. You're all from this. Okay, so identify the variables and express the quantity to be maximized or minimized as a function of one variable. Help me highlight one variable because it will usually come as two. Okay, then differentiate the quantity with respect to the variable. Find the value of the variable that corresponds to the stationary value of the function and check that the stationary value obtained gives a maximum or minimum. Okay, these are the 4 steps. I will go through them slowly, so not to worry. I will go through them slowly. Okay? Okay. Okay, so this one is very hard. Maybe this one. Let me go Something easier, something easier. Okay, I should start at 5.1 first. Okay. This triangle here has a right angle at Z. Okay, now the shape of the triangle varies, but the sides YZ and XZ have a total length, fixed length of 10 cm. Now the length of YZ is X, find the maximum area of the triangle. Now what I want to tell you is actually the maximum area of the triangle is when the triangle here is shape isosceles. Okay, meaning this angle is the same, where it's 45 degrees. Okay, so identify the variable. Now you see, okay, if I want to find the maximum area, you agree with me? That means it's like there is this particular x, there is this particular x, there is this particular area, there is this particular area, there is this particular x. Okay, when I vary the x, there is this particular x that can give you the highest area. Do you agree with me on this? Okay, ma'am? So for example, if x is 1, this will be 9 and 1. If x is 2, it will be 8 and 2. If x is 3, it will be 7 and 3. So if your x changes, your area can change. Okay, so now I want to know which x value can give me the maximum area. So far, okay? Which x value can give me the maximum area? And what I see is that, if I look at this area, do you agree with me at this point, the A, let's say I call this A, the x should be equals to 0, correct? Equals to 0. Why? Because it is the what kind of point? Nathaniel, what kind of point? Maximum point. And it's a stationary point. So how do I find the maximum area of the triangle? It's by identifying the x that can give me the x equals to 0. So far, okay? So same like stationary point. First of all, I find the A in terms of x. You see, in terms of one variable. Easy, right? Easy, huh? Okay, now after that, I differentiate. This is exactly like stationary point. I'm finding the stationary point. Okay, I find that, oh, when equal to 0, x turns out to be 5. Okay, x turns out to be 5. So when I equate to 0, I find that 5 minus x equals to 0, x equals to 5. Huh? Now next thing, right, when we equate to 0, all this gives us is only a stationary point. Okay, it's a stationary point. At this point, you only know that it's a stationary value. You do not know if it's maximum or minimum. So, Kaden, if I know that it's 5, right, but I don't know whether maximum or minimum, based on part 4, what should I do? Based on last Friday lesson, what should I do? How do I know the nature? Oh shit, you're right. Oh, okay. Kaden, you give me another girl's name. Sinfei? Okay, can. Sinfei, if I do not know the nature, how do I know whether it's maximum or minimum? Second or first derivative test. Okay, also you can use the second derivative, alright, which is just -1. Which is just -1. Because, sure you see, this is dA dx. If I differentiate 5 is 0, differentiate minus x is just -1. Simple, right? And since my second derivative is less than 0, therefore there's a maximum area of 12.5. Okay, since it's less than 0, it will tell you that it's a maximum. It will tell you that it's a maximum. So far, okay? Okay. Yeah. Still cannot see. Okay. I start from here. I go down. Go down. Yeah. Okay, so if you're good, this no need to copy. This no need to copy. Okay. If you're good, right, can you help me look at question? Help me look at question. Okay. Question 5.2 and 5.3 first. After that, I will go through 5.1, so not to worry. What's your noise? What's your